So this week we've introduced a new kind of tree, which is a B tree. And I'm going to be walking through two videos here. The first is creating a 2-3 tree, and the second is creating a 2-4 tree. So we're going to be creating these two trees from this input sequence, 1, 6, 7, 8, 5, 4, 9, 10, 11, 12, 13. Before we do that, let's just look at what would happen if we created this, if we input this sequence into a regular binary search tree. So we would start with a 1, and remember, when we insert into a binary search tree, what we do is we first look for where the node would go, and then if we don't find it, we put it there. So 6 would go to the 1 would be the root. Then we'd insert 6, that would go to the right of 1. Then we'd insert 7, just move this up a little actually. That would go to the right of 1 and the right of 6. Then we'd insert 8, which is to the right of 6, to the right of 7. Then we'd insert 5. 5 is to the right of 1, but to the left of 6. Then we'd insert 4. 4 is to the right of 1, to the left of 6, and to the left of 5. Then we'd insert 9, which is to the right of 6, 7, and 8. And we're going to continue down this path to insert 10. I'm going to run out of room on my screen here. 11, 12, and 13. So this is what my binary search tree would look like if I input that data in that particular sequence. And you can see that it's very unbalanced, right? We have everything is on the right subtree of 1. 1 has no left subtree. And this right subtree is very, very long. In fact, if this had been sorted data, it would be even more unbalanced, having this right subtree be even longer. So this is the problem that we run into with just regular binary search trees, is that depending on the input order, we can get very, very unbalanced trees, as you can see here. So one approach to keeping a tree more balanced is to keep it balanced as we add things to the tree. And we can do that through the use of B trees. So let's now create one particular B tree. Oops, before I do that, in specifically a 2-3 tree. But before that, let's just define what a 2-3 tree is consisting of. So this is a regular binary search tree, and each one of these nodes is a 2 node. Now this is a little bit confusing because the 2 refers not to how many pieces of data are stored in the node, but how many children the node can have. So remember, in a regular binary tree, which would include all binary search trees, each node has a single piece of data, and it can have at most 2 children. So this node here has a single piece of data, 6, and it has 2 child nodes, 5 and 7. So all of our nodes we've been talking about up until this point are 2 nodes. And again, that's because they can have 2 children. So keep that in mind. Again, that can be a little confusing because the 2 refers not to the number of data that is stored inside the node, but the number of children. So a 2 node stores only 1 piece of data, but has 2 children. A 3 node can store 2 pieces of data and have 3 children. Okay, so that number that defines the node defines the number of child nodes, not the number of pieces of data that it stores. So a 2-3 tree is a tree that consists of 2 nodes, which are the nodes we've been talking about all up until now, and 3 nodes. And remember, a 3 node is a node that can have 2 pieces of data and 3 children. Okay, so that's the kind of tree we're going to create first. And the general rule for creating a 2-3 tree, as described in the notes, is to always add new data as leaves. Okay, that's the key point here. So what we do is we search for where the leaf would go and we add it. And if we're adding it to create a 2 node, then we're all set, we're done. If we add it to create a 3 node, meaning a node with 2 data elements and 3 children, then we add it and we're done. But if where that leaf should go would create a 4 node, which means a node that would have 3 pieces of data and 4 children, what we do is we kind of pretend to add it there because that's where it belongs. But in a 2-3 tree, we're not allowed to have 4 nodes. So what we do is we then split. And to split, we bump the middle value up into the parent node, and we create 2 child nodes out of the remaining data. So let's take a look at what this looks like. Okay, so we're going to start with our root 1. Next up to add is 6. So what we do is we search for where the 6 would go. The 6 would go and this inside this leaf here because we're allowed to have 3 nodes, which again means a node with 2 pieces of data. So what we'd want to do is in order to add the 6, we'd want to add it here. So this is now a 3 node because it has 2 pieces of data and it potentially can have 3 children. The child off to the left would be any nodes less than 1. The child in the middle would be any nodes between 1 and 6. And the children to the right would be any nodes greater than 6. Okay, so that's an example of a 3 node. Again, 2 pieces of data and 3 children. Any children over here are going to be less than 1. Any children here are going to be between 1 and 6, and any children, and by children I mean subtrees, here are going to be greater than 6. Okay, so that's what, and this here is a, I'm not going to bother adding a label. This here is a 3 node, again, because it has potentially 3 children. Okay, so there I've added my 1 and my 6. Next up is to add 7. So what I do is I search for the leaf where 7 would belong. Now 7 would belong here. Okay, it would belong here to the right of 6. But what I've done now by putting that 7 there is I've actually created a 4 node. Because a 4 node would look like this and it would have 3 pieces of data. Any subtrees or children over here would be less than 1. Any children here would be between 1 and 6. Any children here or subtrees here would be between 6 and 7. And any subtrees off to here would be greater than 7. So this would be an example of a 4 node because again it has 3 pieces of data and 4 children. But in a 2-3 tree, 4 nodes are not allowed. So what I do is I kind of pretend that I created a 4 node because that tells me where the new element belongs, and then I do a split. To split, what I do is I create a new node. Basically, it's a little tricky to do to show here, but I basically bump the middle element up to the new parent, and then I split these values, the 1 and the 7, into singleton nodes. So this is how I'd create my new tree. Okay, so I pretended to create a 4 node of 1, 6, 7, but that's illegal. So I bumped the 6, I split, meaning I bumped the 6 up to be the parent, and the 1 and 7 are now singleton childs. So this is what my tree would look like after inserting these first 3 data points, 1, 6, and 7. All right, so next up, down a little, next up is my 8. So to insert the 8, what I do is I first look for the leaf where it belongs. So the 8 belongs to the right of 6, so I go into the right subtree. The 8 belongs to the right of 7, and 7 is just a 2 node, so I add it right into that node. So this is now a 3 node, and that's legal. That's allowed to have in a 2-3 tree, so I'm done. So this is what my tree looks like after inserting 1, 6, 7, and 8. I now want to insert a 5. So I first, again, search for the leaf where it belongs. So it belongs to the left of 6, so I go into the left subtree. This is a leaf, and it's just a 2 node, so I can insert it there. So I insert it into this node, creating a 3 node. That's allowed. So this is what my tree now looks like. Now this tree right here is what's called ripe for splitting, which means that no matter what I add next is going to require a split. Because when I add things into a 2-3 tree, I always add them to the leaves. A common mistake I see people making is adding something here, like turning this from a 2 node into a 3 node. That's not how you add things to a 2-3 tree. You always add them at the leaf level. So no matter which leaf I add to here, it's going to create an illegal 4 node, and so I'm going to have to do a split. So this tree right now is ripe for splitting, meaning, again, no matter what I add next, I'm going to need to split. So next up to be added is the 4. So what I do is I search for the 4. 4 belongs to the left of 6, so I go into the left subtree, and I hit a leaf. So I add the 4 here. 4 would go in between the 1 and the 5. But that creates an illegal 4 node. So I only pretend to add the 4 here, and now what I really need to do is I need to split. And remember, to split, we take the middle node and we bump it up a level. So I'm taking this 4, bumping it up into the parent, and then the 1 and the 5 get split. So the 1 becomes a singleton node, and the 5 also becomes a singleton node. So this is the tree that I'm left with. This is a valid 2-3 tree because it consists of all 2 nodes and 3 nodes. This is a 2 node, this is a 2 node, this is a 3 node, this is a 3 node. And it's also a valid 2-3 tree because it maintains all of our search properties. So this is a node that's less than 4. Everything in this middle subtree is between 4 and 6, and everything in this right subtree is greater than 6. Okay, so this is what our tree looks like after inserting up to 4. So next up is the 9. So what I do is I again search for the leaf where the 9 belongs. So I start here, 9 is greater than 6, so I go into the right subtree, and here I hit a leaf. So I'm going to insert my 9. Pretend to insert it there, but by inserting the 9 into that leaf, I again have created an illegal 4 node. So I need to do a split. In order to do that split, what I do again is I bump the 8 up a level. And then I turn these back in, the 7 and the 9, into singleton nodes. So, or 2 nodes, I should say. So this is going to be a 7. And I would also create a 9. But now in doing that, I have accidentally again created an illegal 4 node. So I need to do another split. So I need to create another node, bumping the middle up, and allowing the 4 and 8 to be singletons, or 2 nodes. And let me just relink everything up here. The 4 is going to maintain its left and right subtrees, and the 8 is going to maintain its left and right subtrees. So the 4 is going to point to here and here, and the 8 is going to point to here and here. Okay, so that's what happens after I add that. And what we see now is we have a node. Again, it's a valid 2-3 tree because everything is either a 2 node or a 3 node. In this case, everything is actually just 2 nodes. And it's a valid 2-3 tree as well because it maintains our search properties. So everything to the left of 6 is less than 6. Everything to the left of 4 is less than 4. Everything to the right of 4 is greater than 4. Everything to the right of 6 is greater than 6. Everything to the left of 8 is less than 8. And everything to the right of 8 is greater than 8. Okay, so this is what our tree looks like now. So now we're going to add on our next element, which is going to be a 10. So what I do is I first search for where the 10 would go, search for the leaf where 10 belongs. So 10 is greater than 6, so I go to the right. 10 is greater than 8, so I go to the right. Here I find a leaf, and I insert it into that leaf. That creates a 3 node. That's allowed, so I'm done. Next up, I add the 11. 11 is greater than 6, so I go to the right. 11 is greater than 8, so I go to the right. I find a leaf. The 11 would belong here to the right of the 10. But again, now I've created an illegal 4 node, so I need to do a split. To do the split, I move the 10 up into the parent. And I split the 9, 11 back into 2 nodes. So we get a 9 there. And an 11 here. And I'm done because that still has created, what I've done is in my split, I only created a 3 node, and that's allowed. So I don't need to do any more splits. And we can again see that this maintains our properties in that the left subtree is less than 8, the middle subtree is in between 8 and 10, and the right subtree is greater than 10. So it maintains all our properties. So next up we add the 12. 12 is greater than 6, so I go to the right. Here I encounter a 3 node. 12 is greater than the 10, so I again go to the right. And here I encounter a leaf, so I add my 12. When I add the 12, I've created a 3 node. That's allowed, so I'm done. I don't have to do any splitting. Next up, I add the 13. 13 is greater than 6, so I go to the right. Greater than 10, so I go to the right. Here I find a leaf, so I add in where it would go. But in doing that, I've created an illegal 4 node, so I need to split. So in splitting, I bump the 12 up a level, and I create 11 and 13 as, oops, 2 nodes. Okay, but then in doing my split, I've created again an illegal 4 node. So I need to do another split, and to do that, I bump the middle node up, the middle element up a level, bump the 10 up, and create the 8 and 12 as 2 nodes. And then let me again just link up all of my children nodes here. Just rearrange this a little. So the 8 is, this is going to be linked to here. This is going to be linked to here. This is going to be linked to here. And this is going to be linked to here. So this is a little bit messy, but you can see that this is the tree that we would create. It's again a valid, oops, it's a valid 2-3 tree because all of our nodes are either 2 nodes or 3 nodes. Right? All of our in this example, sorry. In this, oh my goodness, I can't move this node. In this example, all of our leaves are 2 nodes. Our interior nodes are 2 nodes, and our root is a 3 node. But as long as we have 2 nodes and 3 nodes, that's legal. And everything to the left of the root node here is less than 6, so that's good. Everything in the middle subtree is between 6 and 10, so that's good. And everything in the right subtree is greater than 10, so that meets all those properties. And we can do the same check with the next level. So everything to the left of 4 is less than 4, to the right, this actually is to the right. Kind of hard to show, I'm running out of room here. Everything to the right of 4 is greater. For the 8, everything to the left is less and everything to the right is greater. And for the 12, everything to the left is less and everything to the right is greater. So this would be the final result of our 2-3 tree that we'd create from this insertion sequence. So again, the general rule of thumb is to search for the leaf, very important there, search for the leaf node where the new value belongs. And if you find that leaf, if that leaf creates a 3 node, meaning a node with 2 values, then you're done. You don't have to do anything. But if when you find that leaf and you do your insertion, you create a 4 node, meaning a node with 3 values, you have to do a split. And to do that split, you take the middle value and bump it up 1, take the remaining 2 values and create individual nodes out of each of them. And then you just need to check again and say, okay, by bumping that value up, did I create another illegal 4 node? And if I did, then I need to do another split, again, bumping the middle value up and creating individual nodes out of the other 2 values. Okay, so that is an example of creating a 2-3 tree. There's a question on the discussion board asking you to create your own 2-3 tree out of a string of letters. So give that a try and post your answer or your questions about that to the discussion board.